guys, here we meet again. I hope part 1 was helpful to you in terms of changing the way the force is applied affects the normal force. If the force is acting parallel to the surface, or force acting at an angle, pulling the object, or force pushing at an angle, how will that influence the normal force and the kinetic friction force thereof? So today we'll look at part 2. In this case, we are going to look at inclined planes. So I'm going to demonstrate with only two scenarios. So I have scenario A. In this case, in scenario A, we have a block of mass M. We are going to take it as 2 kilograms so that we do the actual calculations and we can have a better comparison in terms of the kinetic friction force. So the F applied is pulling the block upslope. The angle of the incline is 10 degrees in this particular case. Now let's look at scenario B. The same object is pulled by the same force, but this time the angle of the incline has been increased. So we're going to determine in which of these two scenarios is the kinetic friction force going to be the smallest way to become much easier to move the object up the slope. Now let's start with drawing the free body diagram. I would always advise you to start with a free body diagram when dealing with mechanics because it becomes much easier to see all the forces acting. Now, it is also important to include, in fact, you must show the components of the weight when you draw the free body diagram so that all the forces are visible on your diagram. So the object is going to be shown by a dot. Then we have forces acting on that dot as arrows pointing away from the dot. So this one is the applied force pulling the object. Then we'll have the normal force. And the normal force, when you draw it, it must make an angle of 90 with the surface. Then the weight, I was supposed to be drawing it pointing vertically downwards here. But now because I want to include its components, I'm going to draw the FG parallel, which will point downslope. So this is our FG parallel. Then there is kinetic friction because the surface is rough. Then I'm going to draw the perpendicular component of the weight, FG perpendicular. Now, if you see that your forces are not joining the dot properly, you can always increase the size of the dot so that all forces emanate from that dot, showing that they're acting on the object. Now, in this case, the acceleration of the block is upslope. So the normal force is in equilibrium with the perpendicular component of the weight, FG perpendicular. So we can say the normal force will be calculated by the following. Normal force will be equals to the FG perpendicular. So this FG perpendicular is given by the mass, acceleration due to gravity, and the cos of theta. Now, because the mass does not change as the block is going up between these two scenarios, what changes is the angle theta. So we are going to find the relationship between the normal and the cos of theta. So we are going to say normal force is directly proportional to the cos of theta. So that means whatever happens to the cos of theta, it will directly influence the normal force. If the cos of theta increases, normal force increases. Then how will this normal force affect the kinetic friction force? So if we look at the formula for kinetic friction force, it is given by the coefficient of kinetic friction force multiplied by the normal force. Now, because this coefficient is constant, that would mean the kinetic friction force is directly proportional to the normal force. So if the normal force increases, the kinetic friction force will also increase. Now, the angle of the incline given here is 10 degrees. So let's look at what the outcome of cos of theta will be. So the cos of theta, in this particular case, it is a cos of 10 degrees. It will be given by, you then use your calculator. Cos of 10 degrees will give you 0.98. So you have your 0.98. Now we look at scenario 2. The free body is still exactly the same, so the normal force is still given by the FG perpendicular, which is given by mg cos of theta. So let's look at what happens to the cos of theta if the angle has increased to 40 degrees. So the cos of theta in this case, which is cos of 40 degrees, will be equals to, you use your calculator to find the cos of theta. In this case, cos of 40 degrees. So that will give you 0.77. So you have 0.77. So clearly, as the angle increases from 10 to 40, the outcome of the cos of theta has decreased. So this is going to decrease the normal force, because remember the normal force is directly proportional to the cos of theta. So if normal force decreases, this is going to decrease the kinetic friction, because the kinetic friction is directly proportional to the normal force. So that will mean scenario B will have a much smaller kinetic friction force compared to scenario A. If we can just quickly do that calculation here so that we can have a clear picture of what happens in terms of the values. So the kinetic friction force given by the coefficient times normal. Say for argument's sake, the coefficient of kinetic friction in this case was given as 0.5. So we'll come and put that 0.5 here. We have 0.5 multiply by. Now the normal force, you can calculate normal force separately. It will be given by mg cos of theta. Now your mass in this particular case is 2 times 9.8 times the cos of 10 degrees. So when you use a calculator, you have 2 times 9.8 times cos of 10. This will give you 19.3. You got 19.30 newtons. So you come and substitute that 19.30 here. Then you multiply it by the coefficient. So 19.30 multiplied by 0.5, that gives you 9.65. Now you have 9.65 newtons. Now if we do the same calculations for scenario B, the kinetic friction force given by coefficient of kinetic friction multiplied by normal. The coefficient of kinetic friction force is still the same value, given by 0.5. So we have 0.5 multiplied by the normal. In this particular case, we have normal is mg cos of theta, so that is 2 times 9.8 multiplied by the cos of 40 degrees in this case. This will give you 7.551 if you round off to 2 decimal places, newtons. Now if you compare this value and the calculated value for scenario A, you can see the kinetic friction force is much larger here, and in scenario B the kinetic friction force is reduced. So that means it will be much easier to move a block in this situation than to move a block in scenario A. Just remember that changing the angle of incline will change the normal, and that will change the kinetic friction force. However, it will not affect the coefficient of kinetic friction. The coefficient of kinetic friction will only change if the surface, the type of material or the surface is changed. That's when it's going to change. Thank you very much. I hope this video will also assist you in understanding the kinetic friction force and how it's influenced by the gradient or the steepness of the slope or the changing angle of the slope. Thank you very much.